So we go to chapter 4 today. This chapter is luckily it's not so long, so we can finish today actually. Chapter 4 today we talk about physical properties of milk. And then in this chapter we discuss physical properties of milk. The density is the mass or the weight of a unit volume. Okay, this is density. For example, like density of water is 1 gram is the weight per milliliter, or 1 kilogram per liter at 20 degrees C. For example, this is the density of water. So we discussed the density of milk, the dry matter, the total dry matter of milk, the freezing point, acidity of milk, redox potential. Redox means reduction oxidation potential, là thế oxy hóa khử. And then the NIR. NIR is near infrared. Now we go first to density. I already mentioned density is the weight, is the mass of one unit volume. So this can be used to convert between volumetric measurements and gravimetric measurement, between the measure of volume and the measure of weight, of mass. So if we know the density, if we know the volume, we can calculate the mass. Or if we know the mass and density, we can calculate the volume. Or if we know these two parameters, we can calculate the density and so on. So we can convert between this and that parameter. And the density is temperature dependent. It's dependent on temperature. When temperature is increased, then the density is increases or decreases the density. What do you think? Nobody answer. If you want to answer, you can always switch on your phone, your microphone, and then you can answer. Okay. So when the temperature is increased, then the volume will expand, right? The volume of a liquid expands while the mass is the same. So then the density will be decreased when the temperature is increased. You remember, so the temperature is temperature dependent. So when they give a density of a liquid, of a solvent, and so on, they need to also give the temperature. And normally the reference temperature to measure density is 20 degrees C. And at this reference temperature, the density of milk is 1030 kilogram per cubic meter. The density of pure water is 1000 kilogram per cubic meter, or 1 kilogram per 1 liter, if we already said. This is the density of pure water at 20 degrees C. This is the density of milk. It's 1030, means that the density of milk is higher than that of pure water, because milk doesn't contain only water but also contains a number of dry matter components like proteins, like lactose, minerals, and so on. So they contain several components which are heavier than water. That's why the total density of milk is higher than that of water. The composition of milk is influenced by a number of factors we already discussed. So that is why actual density of milk is in a range of value from 1027 to 1033. But 1030 is the average density of milk. Right. And the density of milk is dependent on composition of milk, of course, and then it can be calculated based on the density and mass fraction of each component. For example, we already know that milk contains 4% of fat. We know the density of fat, like 4.6% of lactose. We know the density of lactose, and 3.3% of protein. We know the density of protein. So we can actually calculate, okay, based on the percentages and based on the density of each component like that. There's a question here. So when we remove fat from milk, when we remove fat globules from milk, then we obtain scientifically called plasma, but in industry it's called skimmed milk. When we remove fat globules, we obtain skimmed milk, which means the milk we remove the fat. In Vietnamese, this means sữa gầy. Yeah. So what will happen with the density when we remove fat globules? Or density of skim milk and density of whole milk or whole fat milk, which one is higher, do you think?
I think it's whole milk. It's higher.
The answer should be opposite because fat has a low density. Actually, it's lower than the density of water even. So when we remove the fat, we remove the low density component, so the remaining will be higher in density. So skim milk has a higher density compared to whole milk. What happens if we add water into milk? What happens with density? What do you think? The density of milk is 1030. The density of water is 1000. So when we add water into milk, then actually we reduce the density because we add the lighter component. Why do we need to know the density? Because in reality, there are many cases of adulteration. We will discuss this again in some slide. Adulteration means kind of like cheating. Okay, so some not so honest people, they try to add water into milk so they can sell it for a higher volume, right? But so we know that when adding water, we reduce the density. So if we just measure the density, if we see that the density is abnormally low, lower than normal, then we can guess that's what something wrong with this milk already. That is why we study this chapter. And the table will list the density values of typical milk and dairy products. This is whole milk. Whole milk is also called whole fat milk. The milk is from beginning. Okay, fresh whole milk, the density is 1030 kilogram per cubic meter. Heated standardized milk, when we do not change anything, then the density doesn't change. Now, skim milk is the milk when we already remove the fat globules, we remove the fraction of lower density. So now the density of skim milk is a little bit higher than that of whole milk. And you see cream. Cream means a fraction that which have higher content of fat globules, higher content of fat. When you have more fat, like for example, cream of 20% of fat, the density is now almost going down to 1000. If you have cream of even higher fat, so the density even now becomes smaller than the density of water even, because fat has smaller density if we already know. Okay, right, so here we look at evaporated milk at 26% of solid matter. Evaporated means the milk we already evaporate part of water. We remove water, so we have more solids content, more solid matters. We have up to 26%. More solids means that the density is now significantly higher. If we evaporate more to remove more water to have more dry matters, more solids, then the density even become higher now. And then this is for sweet condensed milk. Sweet sweetened or sweet condensed milk is a milk after evaporation. People add sugar. When you already remove part of water and now you even add sugar, which has high density. So now you see the density of this milk is really high. Now it's 1300 already. So when you hold in your hand a can of sweetened condensed milk, you will feel that it's very heavy, much heavier than water. Okay, because the density of milk, of sugar is high. Right, so we go to the second parameter, the dry matter. How to determine dry matter? I think you already did the laboratory exercises about determination of dry matter. How did you do it? We take a sample, put in a cup, in a dish and put in an oven and set at normally 105 to 107 degrees C at this high temperature. And then we put here, we dry up to the minimum weight that we obtain. Okay, we dry. It can be like 4 hours, can be 5, can be 6 hours, depending on the properties of the sample. It take a long time when we do like that, so we remove as much as possible water. The remaining is called dry matter, and this is a reference method to determine dry, okay, up to the point that you remove as much as water. And then the remaining is called dry matter. So dry matter has a major influence on physical properties of milk, of course, because important is also determining the properties of the dairy products that we process. Okay, we process cheese, we process many products. The dry matter influence a lot. And the average dry matter content, the dry matter in milk is 12.50%. This is the average dry matter content. So the other one is the 87.5% would be the moisture content. Okay, when we do dry in like this, the remaining is called dry matter, and the part that is removed is called moisture content. We already know actually moisture content of milk. Dry matter content can be calculated from some characteristics by the Netherlands formula. I mean, there is a formula to estimate dry matter content of milk based on the fat content and the density of that milk at 20 degrees C. If we use this method, this is a reference method, this is a good method, then it takes quite a long time. It's like can be 3, can be 4 hours, can be even more. So they develop another formula to estimate the dry matter content after we measure the density of milk. To measure density, we just use a small tool like this. It's quite simple. It's very simple, and in the lab, when you do in the lab, you will see you have a chance to learn how to measure the density. It's like a matter of 1 or 2 minutes, you can already obtain the density. And for the fat content, there are a number of methods also which also require not long time like this methods. So when you measure this fast, you measure this also quite fast, you can determine the dry matter content by this formula. Okay, now we go to the third physical property, the freezing point. Freezing is a process to convert from liquid into solid. Okay, what is freezing point of pure water?
0 degrees.
Okay, the freezing point of pure water is 0 degrees C. So the freezing point of milk should be lower or higher than 0 degrees C, do you think?
Lower.
Lower.
Lower than 0 degrees C, because milk contain not only water but also many dissolved components which are soluble in milk. And when they are soluble, means they like water. They have affinity, I mean they have some linkage, they have some binding with water. They love water, they link with water. So it's become more difficult for the water to freeze. Difficult for the water to freeze, means the freezing point become lower than that of pure water. Right. So I have an example, but before that, we just look at the first sentence here. Freezing point is determined or is influenced by the molarity of solids rather than the percentage by weight or volume. What does that mean? Just to look at this example. I have a solution here which contain a solution of water, contain 5% weight per weight of sodium chloride. And here I have a solution of 5% also weight per weight of sucrose. Okay. I have two solutions of the same percentage of dissolved component, but just they are different solute. What solution has the lower freezing point, do you think? Sodium solution, sodium chloride solution, or sucrose solution? We have lower freezing point.
Sodium chloride solution.
Why? Why do you think sodium chloride solution will have lower freezing point?
Because the salt molecule has higher affinity with water than the sucrose, so it requires more energy to turn the water into ice compared to the sucrose solution.
Okay, we can explain based on this sentence. The freezing point is determined by molarity rather than by weight, by percentage of weight. Here they have the same percentage of weight, but the molecular weight of sodium chloride is smaller than the molecular weight of sucrose. Means that the molarity of this solution is higher than the molarity of this solution. Molarity means the mole, okay? Mole per volume. But mole means just the mass. You divide it by the molecular mass. And here you have the same mass, the same 5 gram, the same 5% 5 gram. But the molecular weight of this one is smaller. So you have higher number of moles for sodium chloride. So you have lower freezing point for this one. You get it now? If you go to a supermarket and you buy ready to cook ingredient for hot pot, for example. So here they put some vegetable and some fish, some squid, some shrimp, and there's a bag of sauce. There's a bag of sauce for you to cook. Okay, and then they sell this in the supermarkets under freezing condition, frozen condition. And when you hold this, you will see that everything exactly frozen, the fish, the vegetable, carrot, and so on here. So you went to the supermarket and you buy this, and what do you see that the vegetable, the fish, and everything is frozen, but this bag of sauce is still like liquid, still not frozen. Okay, why it's not frozen? Because this sauce is concentrated with a lot of salt, fish sauce, for example, sugar. Okay, this sauce contain like sugar, some organic acids to make it sour, like a lot of sodium chloride, so many dissolved components inside. So that's why this bag is still liquid, not frozen, even though they put this in a freezer. So you check and you see, and don't get panic why it's not frozen. It's not frozen because it contains so high concentration of dissolved components. So the freezing point will be very low. The freezing point of this one lower than the temperature of the freezer. For example, the temperature of freezer is 12 degrees C. The freezing point of this sauce can be like minus 20, for example, as will not get frozen when you put in the freezer like this. Okay, so they measure the freezing point. They can use this as a constant to determine if water has been added into milk, or if milk is okay, or milk has been already added with water. Because if the farmer add water into milk, then we will have higher freezing point. The freezing point will go up to become 0. There is another concept here we should know. It's called freezing point depression. So when they measure the freezing point of milk, they very often use this term freezing point depression. Means how low the freezing point of milk compared to the freezing point of pure water. So here, if the freezing point of pure water is 0, if the freezing point of milk is minus 5.2, for example, degrees C, so the gap, this difference is called freezing point depression. So when we add water into milk, we increase the freezing point. It's going nearer to 0. We increase the freezing point, but we actually reduce the freezing point depression. Remember the term. Okay, and the freezing point of milk is determined by the main dissolved components like lactose and salts. These are the dissolved components in milk and determine the freezing point. The average freezing point of milk is minus, remember, minus 0.52 degrees C. There is a range. This is a range, but this is the average. So if you look, it's minor, means that it's lower than 0. So the freezing point is lower than the freezing point of pure water. We already mentioned many times. If the freezing point of normal milk is known, then we can estimate how much water, the percentage of water has been added to the milk. We can use this formula to calculate. So W is the percentage of added water in suspect milk. C is the actual or the reference freezing point of normal milk. And D is the freezing point of the suspect milk. You measure the freezing point of normal milk. You measure the freezing point of the suspect milk, the milk that you guess that they has added with water. And then S is the percent of total solids in the suspect milk. You measure the dry matter content of the suspect milk and so on. Then you can calculate how many percent water has been added. So there are now already 2 ways that we can measure, or actually 3. We can measure the density, we measure the dry matter, we measure the freezing point. All these 3 methods we can measure and we can determine if milk has been added with water. And then you ask a question, why we need a lot of to determine that. Do people add water to milk often? The question is actually yes. Now, if we don't measure, if we don't analyze, if we don't control very well, so actually people often add water to milk so they can earn more. They sell with a higher volume, for example. Now, there's a question here. Soured or fermented milk has a lower or higher freezing points compared to fresh milk. What do you think? Fermented milk, like yogurt, for example, or some liquid yogurt, for example, when it's still liquid, so you can observe easily. Liquid yogurt, or when you ferment milk into yogurt, then the freezing point is lower or higher. What do you think? When we do fermentation of yogurt, then we will ferment or we will convert part of lactose into what? Lactic acid. Okay. And when this conversion occurs, 1 mole of lactose is normally converted to 2 moles of lactic acid. So when we do fermentation, we doesn't change the concentration of dry matter based on percentage, but actually we increase the molarity, the number of moles that we increase. When we increase the number of moles, then we reduce the freezing point. So the freezing point of fermented milk is lower than the freezing point of fresh milk. Remember, okay. Freezing points are not a reliable index for added water in processed milk. When we already process, when we already do heat treatment, so measurement of freezing point to determine if water has been added or not has been added, then it's not accurate. But on fresh milk, on raw milk, yes, we can do. Right. Okay, so we go to the next property, acidity. When we have higher acidity, means we have lower pH value and the milk becomes sour, right? So if we take milk from a cow and then we leave at room temperature for a while, then the fermentation will occur in this milk and then the pH will decrease and the acidity then increase. So acidity is an important parameter for its quality, for the quality of milk. If the acidity is higher than normal, then we can conclude that this milk is not fresh anymore. It has been stored at not good temperature for a while, so the fermentation, the sour fermentation already occurs. It's also a characteristic for fermentation processes, means that, for example, during fermentation of yogurt, then pH is an important parameter to illustrate, to explain for the fermentation process. So during fermentation of yogurt, the pH should go down. But during storage of raw milk, then pH should not go down, should be stable. Okay, fresh milk normally has pH from 6.6 to 6.8. This is a normal pH values of fresh milk. It's a little bit acidic. The neutral pH is 7. When it's below 7, you call this acidic. When it's above 7, we call this basic. And this one is a little bit acidic for fresh milk. It's the same for fresh meat as well. Fresh meat also has this range of about this range of pH. Here we look at the pH of several products, for example, and this is a Docknit degree. The Docknit degree. Degree D is called Docknit degree. This explains the acidity. During fermentation, pH go down, Docknit degree go up, acidity go up. Okay. pH also explains acidity, but in opposite way. So they use another parameter like Docknit degree. Docknit degree is the volume of how many milliliters of sodium hydroxide with the concentration of 109 normality. This is normality to neutralize 10 milliml of milk. So this is a definition of the Docknit. So if the acidity is higher, we need higher volume of sodium hydroxide to neutralize. So this increases. Okay, for fresh milk, the pH is in this range and the Docknit degree is in this range from 16 to 19 degree D. For alkaline milk, which the milk at the end of lactation or the milk from myrtitis cow. If a cow has myrtitis or at the end of lactation as the month 9 or 10 of lactation, then the pH is a bit higher. It's like 6.9. Slightly sour milk, the milk which has been fermented a little bit, then the pH is a little bit lower, while the Docknit degree a little bit higher. So now if we look here and then we go to here, maximum acidification streptococcus. For example, in making yogurt, we have two strains, lactobacillus bulgaricus belong to this one, and we have another one, streptococcus thermophilus. These are the two strains in making yogurt, for example. And here it will tell us which strains can produce more organic acid. Lactobacillus can reduce the pH maximally to 3.9, the other one to 4.5. And 4.5 mean the Docknit degree is 120. 3.9 Docknit degree 250. You see the difference in pH is not so much, but the difference in Docknit degree is quite a lot. So these two are very much different in acidity, but the pH doesn't represent that. And again, we go back. If we look at these two, then lactobacillus can produce more organic acid, can work at lower pH. This one, when the pH go to 4.5, is already inhibited. It cannot do fermentation anymore, but this one can do fermentation further for pH going down furthermore. Just one point to remember. Now we go to redox potential, reduction oxidation potential. This is determined by the presence of oxygen. If there is a lot of oxygen, then high redox potential. If there is not a lot of oxygen, then low, or no oxygen, then low redox potential. Redox potential of milk is in this range, plus 0.2 to plus 0.3 voltage, and is determined or influenced by the dissolved oxygen in milk. So when there is more oxygen, higher redox potential. If we already know. Why we need to discuss this? Because when we know that the redox potential, so we know that microorganisms, that when there is a lot of oxygen, high redox potential, then the aerobic microorganism can grow fast. In other case, when there is not much oxygen, then the anaerobic microorganism will grow, and so on. And this one will be in the lab, the laboratory exercises you will do later, so you will be explained during the lab, you will know it. Okay, and then the last physical property that we discussed is near infrared spectroscopy, NIR. This is the spectra of radiation. The range in wavelength can be from very small to larger. And then there's a large range of radiation. The visible light, the light that we can see, is actually only a small range in this spectrum. For example, the wavelength from 330 nanometer to 760 nanometer. So our eyes can only see in this range, but in reality, it's a lot of radiation with many difference in wavelengths like that. So the light, what is the light here? The light at this wavelength is violet. The light at this wavelength is red. If you already remember. Okay. So here, when the wavelength is down here, and this range, we call it ultraviolet. Because this is violet, so below the ultraviolet. And here is red. So when the wavelength is in this range, higher than the wavelength of red, we call this infrared. This one, this range, infrared. And the near part here is called near infrared. Okay, near infrared is a spectrum. It's in the wavelength, the range just above the wavelength of red light. But when we talk about frequency, so it should go back. Frequency is opposite. When the wavelength is smaller, then the frequency is larger. The frequency is proportional to actually energy. So the energy here is larger and then smaller here. So the radiation from here and down to here have high energy. The one here lower and lower energy. So when you go to a sun bath in a beach, for example, you want to have more sunlight for your skin. So normally you are afraid of this radiation. You use some cosmetic to apply on your skin to prevent ultraviolet, because this radiation has high energy, which may cause some damage to the cells of your skin, may cause damage to DNA and so on, for example. But for this light then normally it's safer. Khi mấy em đi tắm biển tắm đồ là mấy em sợ là tia cực tím chứ không phải là tia hồng ngoại nha. Mình nói hồng ngoại là người ta cười, tại vì hồng ngoại thực là bước sóng nó lớn hơn đỏ, năng lượng nó nhỏ hơn đỏ. Cực tím là bước sóng là nhỏ hơn tím rồi, nên là năng lượng nó sẽ lớn hơn tím rất nhiều. Và từ đây trở xuống nè, thì năng lượng này gọi là năng lượng ion hóa. Khi nó chiếu vào một vật chất, nó có thể làm bắn electron ra khỏi nguyên tố và làm thay đổi điện tích nguyên tố, làm ion hóa nguyên tố vật chất, có thể thay đổi, tổn thương tế bào da đồ này, vân vân. Okay, so near infrared spectrometry cover the range of wavelength between 380 to 3000 nanometer. It's in this range. And then people, they apply the NIR to analyze milk composition very fast. They measure composition very fast. They measure and then they can already determine moisture content, protein, lactose, fat, and the mineral together in one measurement. This is one of the machines, for example. Here you have the small container which contain the milk, and then the machine will suck the milk into a cells, a glass cells, and then they will project in near infrared radiation, and then this will reflect or refract or absorb the radiation that they project in. Then they can measure this. They measure the signal here, and then they can already relate or calculate to the composition of the milk. So depending on the composition of the milk, this behavior of the light will be not the same, and they can measure. When you project a light to a material, part will be reflects, part will be absorbed, and then another part can pass through, okay, can pass through it, and so on, and then they can measure this. And when they measure, and they base on calculation, based on many experiment on the regression and so on, so they measure this and they will know the milk composition. So they know how much lactose or in this milk, protein, fat, minerals, and so on. So they can measure very fast. If you do it manually in the lab, if you do it by human, then you need so many people to measure. But this machine will do very fast. One measurement will take like 1 minute, for example. 1 minute for one sample, and they can give result of many parameters already very fast. So like, for example, in developed countries, there are farms, large farms, and at the farm they have a cooling tank. This is a cooling tank where they store fresh milk, and then the company, the buyer, the company will send the cooling truck. This is truck with a cooling system. They come here and they will pump this milk, and they also take sample of the milk. They take small sample and they bring this sample is sent to this center. The center, this will analyze the milk sample, and we know the quality of the milk. This center will send the result back to the farmer and send the result to the processing company. The company will bring this milk to the factory, and during the transportation like this, they come here, they take the milk from this farm, but the same truck can go here and take the milk from the other farm, because the truck is not full yet. They can take milk from several farms, but before they take sample of the milk, they analyze here, and then when they bring to the factory, before they load into the factory, they have to analyze again. They analyze again to be sure if the milk is suitable for processing, then they will receive into the factory. And based on the of the analysis here, they already signed a contract between the factory and the farmers that depending on the quality of your milk, I will give you a price, money. So normally the money that the factory pay to the farmer is not a fixed, it's not a fixed value. It can change depending on the quality of the milk. If the milk has higher quality, the price is higher. Lower quality, the price is lower. So the center, the third party in the middle here, can analyze and give the result to the two party. Based on that, the factory will pay a certain money to the farmer. Okay. So the center like this can do like analysis of 1,000 sample a day. So many sample a day, so human cannot do it manually. So a machine like this will be very helpful just to measure many sample like that.